Okay. Topic given to me is C13 NMR. As this, most of the students are PhD students, so and maybe from the chemistry background, so they must be aware of the what is mean by C13 NMR, or before that, what is NMR spectroscopy, isn't it? Okay, I think they are not. I would like to have the interactive session, but if it is not feasible, let us have. Now here on the screen, you are observing NMR of C13 NMR of 1-bromobutane. As bromobutane content, the structure has been drawn over here, and bromobutane contains 4 carbon atoms. So you are observing 4 signal in C13 NMR. So in short, the C13 NMR gives you the skeleton of any organic molecule. Okay. So with this introduction, let us move to the next slide. It's not moving. Huh? Okay, before going in detail of C13 NMR spectroscopy, let us see what is mean by spectroscopy. Now, the spectroscopy is nothing but the interaction of light with the matter. And what is light? The light, whatever we are observing, it contributes less than 10% of whole electromagnetic radiation. Okay, so electromagnetic radiation start from the cosmic gamma rays to up to radio frequency. So in between we have the ultraviolet visible light. We usually say it's light. Then we have the infrared region and microwave and radio frequency. If you see all this electromagnetic spectrum, gamma rays and cosmic rays, they will have the highest energy while the radio frequency will have the lowest energy. But if you see the wavelength wise, radio frequency will be the having the higher wavelength, while the cosmic rays will have the lower wavelength. So energy I have shown over here. Energy associated with the cosmic or gamma region is the 10 raised to 4 to 10 raised to 10 kilocalorie, calorie per mole, while that of radio frequency 10 raised to minus to 10 raised to minus 6 calorie per mole. Now, with the highest energy which is there in the gamma and cosmic rays, we will see the nuclear transitions like the nuclear fusion and nuclear fission type of transition can be observed over here. In UV and visible range, we are observing electronic transition like sigma to sigma, sigma star, pi to pi star transition. Here we are observing in UV and visible range, we are observing electronic transitions, which shows a very broad type of spectrum. Coming to the infrared spectroscopy, where we observe the vibrational transitions, while in microwave rotational transition, while the radio frequency we are able to observe the as the energy is very less, this less energy is able enables us to get the nuclear spin transitions. Coming to the various spectroscopic technique and their importance, I just now explain you what is meant by the spectroscopy. So we are taking the sample, which can be dissolved or can be a solid state or can be a gas as well. We are irradiating with radiation. The sample molecules or part of the atoms goes in an excited state. So they absorb the energy and go to the excited state, and we will get the absorption kind of spectrum. Then the excited state molecule comes to the ground state, they emit the energy, and we will get the transmission kind of interaction. So the spectrum we are observing over here. From UV visible region, we used to get information about the chromophore present in a molecule as well as a conjugation in a molecule. So we require here some chromophore. It may be the carbon-carbon double bond, carbon-carbon triple bond, even a carbon-carbon double bond present in aromatic ring, carbonyl groups, nitrile groups, nitro groups, all they are serves as a chromophore. Coming to the IR spectroscopy, we try to find out the different functional group present in a molecule. Coming to the H1 NMR spectroscopy, I hope everybody knows H1 NMR spectroscopy. So we get a good amount of information from H1 NMR spectroscopy. First of all, the number of different type of hydrogen present in a molecule. Then not only the types of hydrogen, but their numbers also we can get it from the H1 NMR. And some hydrogens are attached to the electron deficient molecule or substituent, or some molecules, some hydrogens, they may have in variety donor groups. So in this different electronic environments of hydrogen, we will see different chemical shift. And of course, the spectra, the peaks are sometimes we are getting doublet, triplet, quartet. It's due to the coupling, spin-spin coupling phenomena, which also take care of neighbor-to-neighbor relation, which nowadays we are not taking care because we are staying in isolated flats and nobody want to interact with each other. But please see the NMR. In NMR, at least the proton knows what is there in the next carbon is having how many protons. So that information we get from NMR. So not only the hydrogen we can scan with the NMR, we can scan 13C, nitrogen 15, fluorine 19, 31 phosphorus nuclei from the NMR. Subsequently, we can utilize the NMR for the 2D technique. So if you take all this technique, including UV, visible, IR, and H1 NMR, C13 NMR, as well as 2D, all these techniques, if you analyze very properly, I'm sure you will get the structure of AE unknown compound or molecules. All these techniques are mutually complementary. So if you are taking just C13 NMR, or if you are taking just H1 NMR, whole structure is not possible. But if you take all this spectroscopic technique to find out the structure of molecule, it is very easy to get the structure. Along with this, if we have extracted some compound from natural resources and try to get its molecular formula, in that case, mass spectrometry is very useful technique to get the molecular formula, as well as it can also confirm the structure of the compound. So I hope some of the student, at least they have seen NMR spectrometer, how it is working. So I have shown here at the corner, left corner, one picture for the NMR spectrometer, which we can utilize. Not only the chemist, but biologist also can utilize to get the structure of peptides, proteins, some polymers also you can get it apart from the small molecules. Coming to the small molecules, I have shown at the right corner one H1 NMR spectroscopic technique as well as C13. So these two are there along with the 2D. 2D is also there. So all these techniques are very useful to get the structure of small molecule as well as the polymers. So this NMR is not only useful for the non-living or some artificial molecules, but you can get information if our body, human body has been scanned, and the technique is known as a magnetic resonance imaging, which is called as a MRI technique. So most of the hospitals now, they are equipped with this MRI technique. Now the name has been changed from nuclear to magnetic resonance structure, magnetic resonance imaging, because most of the common people, they are very much afraid of the nuclear term. So as soon as they will say nuclear, we say the nuclear, they are relating with the some radiation, which is we are getting from the atom bomb like kind of thing. So to get rid of this fear, the name is coined as a MRI technique. Now, this MRI technique will also focus nuclei H1 nuclei. Now, this H1 nuclei in our body, where we are going to scan the part of the organ of our body, maybe the if patient has some tumor, you can get the MRI technique. So at the tumor site, you will see the different hydrogen water density will be there, and which we are scanning in MRI technique. Now, I am from the chemistry department, Savitribai Phule Pune University. So we have a long tradition of having this NMR. Various techniques, NMR instrument has been installed here in our department. In 1980s, we have the 60 megahertz instrument. Then we have the 90 megahertz instrument. In 2000, we have 300 megahertz instrument. And right now, we have the 400 and 500 megahertz instrument, which are more sophisticated. So coming to the very old instrument, the picture I have shown is, which is there, uh, in 1960, where we have installed the 40 megahertz instrument. Now here you can see, here we have the electromagnet has been installed over here. So in that NMR we have the electromagnet, and the method we use the um, continuous wave. And the NMR from this instrument will look like this. This is the NMR of ethanol. Now, ethanol contain H1 NMR, of course. It contains three types of protons. So you will see the three big peaks, which gives the information only the different types of hydrogen over there. But coming to the most of sophisticated instrument, like here, now this is the picture of 500 megahertz instrument, where now the electromagnet has been changed by the superconducting magnet. Now, as the magnetic field we have increased, more resolution you can obtain. And here the you are observing the same molecule NMR, but now here the peaks are more resolved and you can get more information from this NMR. This is the picture of NMR machine. If you take the cross section, you will get this picture. So I'm talking about the superconducting coil, which is there, which is nothing but copper and some alloy they are mixing. Now this superconducting coil will have very, very less resistance at low temperature. And this low temperature, we can get it by having the helium, liquid helium over here. So this superconducting coil will be immediately contact with the helium, liquid helium, and this liquid to evaporate, to less down the evaporation rate of helium, the helium divar is covered with the liquid nitrogen divar. Okay, and here somewhere we have the console of that NMR. So we are having the we are dropping the our NMR tube from the up top of this instrument, and it comes over here. Okay, so the main function of this superconducting coil is to give very high magnetic field. Then here at the console we have the radio frequency, which will able to give the transitions. Okay, this is the just to have the idea of what is the temperature of liquid helium. It's a minus 269 degrees Celsius, which is nothing but 4.2 Kelvin. So at this low temperature, the superconducting coil will have very, very less resistance, and it will act as a superconductor. Then we are okay. This liquid helium has to be filled 7 to 8 months, and 100 liter of liquid helium cost around 3 to 4 lakhs. So, and this liquid to less down the rate of evaporation rate of the helium, we are filling liquid nitrogen, which has the temperature minus 196 degrees Celsius. And this liquid nitrogen, we have to fill at least 50 liter weekly. Okay. So to maintain this NMR instrument, it's just like the white elephant we are maintaining over here. Coming to the history of NMR spectroscopy, this NMR phenomenon was first discovered by two groups in 1945. The two groups which are working, one working is Harvard University and another working in Stanford University. One group which is headed by the Purcell, they were working on the paraffin, while the Stanford group, which was headed by the Block, they were working on the water molecule. So both these groups, they have first find out the NMR phenomena. Then in 1950, the first NMR of ethanol was discovered by the uh, group of the scientists, Arnold, Dharamati, and Packard. And we all Indians should proud of that. One of the scientists who scanned the first time ethanol, Dharamati, he was the Indian fellow. And after working in Stanford University, he moves here in TFR Mumbai, where he has developed very nice NMR division at TFR. In 1952, both these scientists, Bloch and Purcell, they were awarded with the first Nobel Prize, which is in physics subject. In 1991, the second Nobel Prize in NMR was awarded to the Richard Ernst from Switzerland, and he has discovered very applied technique, which is a Fourier transform technique. He has been used, and by his addition, we can now you can use the C13 NMR and 2D NMR very frequently. In 2002, third Nobel Prize in NMR was awarded to Kurt Wuthrich for the structure determination of protein and peptide molecules. And the fourth Nobel Prize in medicine was awarded to the Paul Lutherberg and Sir Peter for their invention in MRI technique. So with this history, let us move towards the nuclear properties which we are utilizing in NMR. Now, everybody knows that nucleus contains protons and neutrons. Protons are positively charged while the neutrons are neutral in. So as they are positively charged, they spin always with some axis. Now, the spinning of this charge particle, which is a proton, produces spin angular moment or spin quantum number and magnetic moment and electric quadrupole movement. These three properties are shown by this spinning proton, and these properties we are going to utilize in NMR. Now, in absence of magnetic movement, magnetic field, all these spins of protons are randomly oriented. But when we are placing this proton or this nucleus in very high magnetic field, the magnetic field as the strength is shown by S0. Now this all when we are putting this nucleus in external magnetic field, nuclei get oriented. Okay, some in one orientation you will see that this is the less energy orientation, so it has the same alignment as the magnetic movement, while the higher energy alignment, which is opposite to the external magnetic field. So all the spin will get divided into two orientation. What happens when we fall the radio frequency, which will be the difference between these two energy? Same energy if we fall in the form of radio frequency, the nucleus which has the nuclear spin which is in lower energy will get inverted into a higher energy. And such nuclear spin flipping we are observing when the radio frequency will fall. And this is the principle behind the NMR. Now, will all the nucleus will show this flipping of the spin? No, not at all. So what is the condition to have this NMR active nucleus? Now we have already seen very important property, angular momentum of spinning nucleus, which is also called as a spin quantum number. Now, the spin quantum number is a characteristic constant of a nucleus and is depend on number of protons and neutrons in the nucleus. Now, we have to apply three rules. The first rule, you just take care of, you count the number of protons and neutrons. So nuclei with the odd mass number or odd or even number of protons have half integral such as 1/2, 3/2 or 5/2. So these are the spin quantum number when we have the nucleus with odd mass number and odd or even number of atomic protons. Now you can easily get this number of proton from atomic number, isn't it? And mass number will have the number of protons and neutrons. So we will divide whole all the molecules into three categories. The nucleus with odd mass number, but odd or even protons. Second, nucleus with odd mass number, even mass number, and odd number of protons. We'll have the full integral spin quantum number like 1, 2, 3. And nucleus with the even mass number and even number of proton will have the zero spin. Let us take the example. We have the hydrogen. Hydrogen, the two isotopes are there, H1 and D2, deuterium. So both, in which respect they are differ? They are differ with the number of neutron. Now H1 will have odd mass number and odd number of proton. So it will have the spin quantum number 1/2. Coming to the deuterium, which we also call as a 2H, deuterium will have the one mass number, while its number of atomic number will be the 2, neutron will be 2, and we'll have the spin quantum number 1. Coming to the carbon 12 will have 12 is a mass number, while atomic number is 6. So we have the 6 proton and 6 neutrons. So the spin will get cancelled and the spin quantum number for carbon 12 is 0. While about the carbon 13, 13 is odd number, protons are 6, neutrons are 7. So here carbon 13 will have the spin quantum number 1/2. So which nuclei will be the NMR active? All the nuclei which has the non-zero spin quantum number will be the NMR active. Only the nucleus which has the even mass number, even number of protons will be NMR non-active nucleus. So carbon 13 will be NMR inactive nucleus. Oxygen 18 is NMR inactive, while rest of the nucleus which has non-zero spin quantum number are NMR active. So what are the requirements for the NMR active nucleus? The nucleus should have the spin quantum number I should be greater than 0. Magnetic moment mu should be greater than 0. The other requirement for the NMR active nucleus, they should have the even distribution of charge. That means they should have the spherical nucleus. In that case, you will have Q is equal to 0. And the third requirement, the nucleus should have the very high percentage of natural abundance. Coming to the nuclei with 1/2 spin, will have the magnetic moment greater than 0. This nuclei will have the spherical shape and Q is equal to 0. Examples are H1, C13, 19 fluorine, 31 phosphorus. All will have I is equal to 1/2. And there, except C13, H1 fluorine 19 and 31 phosphorus will have very high percent natural abundance. So these three nuclei we can easily detect. Coming to the C13 nuclei, its natural abundance is just 1.1%. 98% will be of C12, C. So with this small natural percentage of C13, now the scientist has made so progress that we can detect whole skeleton of any organic molecule. These are the percentage of natural. Hydrogen is 99, deuterium is 0.015. So the nucleus which we are targeting is H1 is naturally 99.9%. Coming to the carbon 13, 98.8%, while carbon 13 is just 1.1%. Nuclei with I is equal to 0, like we just talk about the carbon 13 and oxygen 16, they have the I 0 as well as mu is equal to 0. So they will not interact with the applied magnetic field. And hence they are NMR non-active nuclei. Coming to the deuterium and nitrogen 14 over here, deuterium and nitrogen 14 both have the I, that is spin quantum number 1. So this nucleus will have the magnetic moment greater than 0. Q is also greater than 0. And this nucleus will not be a spherical. They will have the different shape like ellipsoid. And we can get the spectrum for this nucleus, but it will be difficult to interpret. Okay. So we have the spin quantum number of hydrogen 1/2, carbon 13 1/2. If such nucleus we kept in a high magnetic field, spin inversion will take place in very high magnetic field, and the energy required you can calculate is equal to by using this formula, delta E is equal to gamma S0 divided by 2 pi, where gamma is gyromagnetic ratio or magnetogyric ratio. Gamma for the H1 is 26.7, while the C13 is 6.7, very, very less. To get the exact frequency, you can use this equation. Mu is equal to gamma into H0 divided by 2 pi. Now, 2 pi is the constant, H0 magnetic field is constant, so the frequency is depend on the gyromagnetic ratio. Coming to the C13 nucleus, now this C13 nucleus is just 1.1% naturally, and remaining is C12 nucleus, which is 98.9%, but which is NMR inactive. Okay, so C13 nucleus is very, very less sensitive compared to the H1 nucleus. The first factor that we already discussed is natural abundance. And the second factor is about the gyromagnetic ratio that we have just seen. Gyromagnetic ratio for the H hydrogen nucleus is 26.7. For carbon 13 is 6.7. If you take the ratio of both these gamma, you will get 1/4. So 4 times gyromagnetic ratio is higher in case of hydrogen, while when we compare with the carbon 13. So the sensitivity we can calculate by using this ratio, gyromagnetic ratio of C13 to H. You take the cube of this, you will get 164. So 64, 1 by 64. And so there is a 64 time reduction in sensitivity of C13 nuclei as compared to the H1. So this is only due to the gyromagnetic ratio. Now, combining effect of natural abundance and gyromagnetic. Natural abundance, the ratio is 1 by 90. It's actually 1.1 divided by 99.98, but let's take the round figure 90. So 90 times, you will say the natural abundance is less as compared to the hydrogen. So sensitivity will also decrease 90 times than H1. So both this effect, if you consider natural abundance and gyromagnetic ratio, if you take these two numbers, you will get 1 by 90 into 1 by 64. So you total reduction in sensitivity will be 1 by 5,760. So let us take 6,000 as a round figure. So sensitivity of carbon-13 nuclei is around 6,000 times smaller as compared to the H1 nuclei. So you just try to imagine how much pains scientists must have taken to get this C13 NMR. So if you have this H1 intensity, if you take the 8 scan, if the H1 intensity will be like this, C13 will be very, very small, 6,000 times less as compared to the intensity of H1. Coming to the how to calculate operating frequency for H1 and C13 nucleus, we require gyromagnetic ratio. Gyromagnetic ratio already I have given 26.7 for hydrogen, for carbon-13 is 6.7. The ratio is 1 by 4. So for magnetic field with 23.5 kilogauss, the corresponding operating frequency for H it will be 100 hertz, 100 megahertz. How to calculate it? I think I have given this equation. You have to calculate, you just fill all this in this equation. Gamma we know, H0 we know. So you just fill and you will get the this number. So with H0 23.5 kilogauss, the H1 nucleus will have the frequency 100 megahertz, while that of gamma of carbon-13 is 6.7. You just fill in the same equation, you will get 25. So carbon-13 will resonate at 25 megahertz with the same magnetic field. Let us increase the magnetic field for H0, that is magnetic field. If we increase to 7 Tesla, H1 nucleus will have the operating frequency 300 megahertz, while that of C13 is 75 megahertz. So you just imagine with the same magnetic field, but the operating frequency of H1 and C13 will be different. For C13, you have to always use 1/4 of hydrogen. Okay? So gyromagnetic ratio of C13, which is 1/4 that of hydrogen, affects two things, sensitivity as well as operating frequency. Okay? So relative sensitivity of C13 nucleus is, again, I'm saying is 6,000 times smaller than compared to H1. Coming to the C13 nucleus, it's a 1.1% naturally abundant. So therefore, acquisition of spectrum usually take much longer time than hydrogen. So the direct observation of this carbon skeleton has been available as a practical basis only since the early 1970s. The carbon-12 nucleus, which is the most abundant nucleus, is NMR inactive. We already know the carbon-13 nucleus, like H1, will have the spin 1/2, but however, it will be less focus until 1970s. The magnetic ratio for carbon-13 nucleus is about 1/4 than the H1. Therefore, resonating frequency is also 1/4 compared to the H1. So at this lower frequency, excess of population of nuclei in the lower spin state is reduced, which in turn reduces the sensitivity of NMR detection. Unlike the H1 NMR, the area of the peak is not proportional to the number of carbon giving rise to that signal. So therefore, we are not using integration in C13 NMR. Each unique carbon in a molecule gives rise to a signal in C13. Therefore, if there are very few signals in spectrum than the carbon atoms in the compound, then you must assume that some symmetry should be there in a molecule. When running in a spectrum, the protons are usually decoupled from their respective carbon. Hence, the carbon 13 spectrum, you always see a singlets. Only one peak you are observing, and this is we call as a P&D spectra, proton noise decoupled spectra. So as I said, the first H1 NMR was recorded in 1952. First C13 NMR was recorded in 1957 again by two groups, Lutherberg and Home. And that time the technology was not advanced, and there are many difficulties to get single NMR. First of all, poor resolution, less sensitivity, and this is only they are scanning first low molecular weight compounds, and one has required very high concentration of sample. For example, for H1 we require hardly 10 to 12 milligram of sample, but for scanning C13 NMR at that time, we are talking about 1950s century, they used to take 500 milligram of sample, very high concentration they used to take. And usually for getting one scan, almost 1 week they are engaging that machine. So engaging the machine for 1 week, it's very difficult. So these are all the difficulties in early 1950s, but in early 1970s, like in 1966, Richard Ernst developed the two techniques, Fourier transform technique and P&D technique, proton noise decoupled technique. Due to these two techniques, major breakthrough occurs. And after 1970s, the scientists are now they are started to use carbon 13 NMR. Now this is coming to the Fourier transform technique. Now the carbon 13 nucleus, they have very long relaxation time. Once we give the pulse of radio frequency, they relaxes their relaxation time very less. So we are due to this Fourier transform technique, we are losing the integration. The quaternary and fully substituted carbons, they have the long relaxation time. So when we are they will not relax completely unless we start the second pulse start. So in this whole steps, we are losing the sensitivity during the repetitive scan, and mixed intensity will be you can get it for the quaternary and fully substituted carbons. While due to the NOE effect, the carbon which has the hydrogen, they have the higher intensity due to NOE effect, and the peaks are intense when the carbon is having the hydrogens. Coming to the second technique, which is a proton noise decoupling technique. I've seen the first NMR of bromobutane, where 4 carbon are there and 4 peaks we are observing. So for each non-equivalent carbon 13, you will get a peak in carbon 13 NMR. The proton coupled C13 NMR spectrum shows a complex overlapping multiplates, mainly due to the coupling with the hydrogen. Now there are different type of hydrogen. If we see the proton couple C13 NMR, one bond coupling means that hydrogen is directly attached to the carbon, we get one bond coupling or direct coupling or 1-2 coupling, and it is present between the 100 to 250. The coupling constant is 100 to 250 hertz. For two bond coupling, uh, the coupling constant is 20 to 50 hertz. For 1-4 coupling, the coupling constant is 10 to 40 hertz. For 1-5 coupling, the range is from 0 to 20 hertz. You must be remembering the coupling constant for the hydrogens. It hardly has the, if you take the olefinic coupling for trans, it comes around 18 to 19 hertz. But here you just see the couplings. So these couplings will make C13 NMR very, very complicated. And therefore, always a significant overlap you will see if we see the proton couple C13 spectrum, and the splitting pattern is very difficult to determine. Let us take the one example. Ethanol, the simple ethanol molecule. Now it contains two carbons, so only two peaks you should observe, isn't it? But how many, if you see the proton couple C13 NMR, you will see 12 peaks due to the CH3 and 12 peaks due to the methylene carbon. Okay, so total 24 peaks you will get for proton couple spectrum. Why 12? Because this carbon is directly attached to 3 hydrogen. So according to n plus 1 rule, 3 plus 1 you will get. And for 2 bond coupling, when this carbon is coupled with this hydrogen, now number of hydrogen are 2. So 2 plus 1. So 4 into 3 gives the 12 lines. Coming to the methylene carbon, the direct attach 2 hydrogen. So 2 plus 1. While 2 bond away, that there are 3 hydrogens, so 3 plus 1 gives the 12 lines. So you just imagine for ethanol, which contain 2 carbon, you are getting 24 peaks for proton couple spectrum. So it is very necessary to have this proton noise decouple technique, and which we call as a PND technique. What we do in PND technique, a sample is irradiated with the 2 radio frequency. Okay, the first pulse will excite all carbon 13 nuclei. The second pulse, which is exactly at match with the hydrogen of TMS. TMS is standard. What it will cause, all protons in a molecule will go in a rapid transition. That means if we have the two transitions, alpha and beta, so the proton spin will just have a rapid transition between alpha and beta spin state. As a result, this carbon 13 will not finding any coupling with the H1. So H1 and C13 spin-spin interaction will not be observed. So heteronuclear spin decoupling we are removing. Now someone may ask me that heteronuclear, now what about the carbon-carbon? Whether in ethanol we have the two carbons, whether they are directly bonded, why not you will get a doublet from that? No, it is not possible, because the whole as we already seen that we have only the natural abundance is 1.1%. So in a molecule containing carbon 13 isotope, it is unlikely that a second atom in the same molecule will be a carbon 13 atom. For example, we have the ethanol. It is very difficult. Okay, suppose this carbon is carbon 13. It is very difficult to have adjacent carbon also carbon 13, because natural abundance is just 1.1%. Therefore, when we observe the carbon 13 spectrum, we are observing a spectrum built up from collection of molecules in which each molecule supply no more than a single carbon 13 resonance. So please remember, no single molecule supplies a complete spectrum. As we have seen from the H1, in H1, you have the 99% abundance. So you can get whole spectrum from single molecule for the H1, but it is not possible for carbon-13 nucleus. So due to the P&D technique, all the multiplets which may be you will get due to the proton coupling will collapse into a singlet. You may have the triplet, doublet, or quartet, they will collapse into a singlet. One more advantage due to this P&D technique, the signal noise ratio will be increase, and you will get that signal will be more enhanced by using P&D technique. Okay, so if you want to see the schematically, this is the simple pulse sequence. We are giving a pulse, then we have the acquisition time. We give the some time for relaxing the nucleus, and then we give the second pulse, which we are doing in H1 NMR. But in case of C13 NMR, proton noise decoupled spectra, we are giving the two pulses. One pulse will excite carbon-13 nucleus. We will have the acquisition time. During that, carbon-13 nucleus will get relaxed, and then the second pulse will be there. But here, the second pulse will irradiate H1 nucleus. They will transit between alpha and beta spin, and hence carbon-13 will not find any coupling nucleus, any nucleus for the coupling. So all this multiplet will turn into a singlet. So this is the spectrum of 1-bromo-butane. Let us compare the interpretation of H1 and C13. For H1, we have the three important parameters. First of all, integration, which gives the number of hydrogen, chemical shifts, which gives the electronic environment of the nucleus, and the coupling constant will able to get the find out the coupling nucleus. In case of carbon-13 NMR, due to the Fourier transform technique, integration is we are losing. Coupling constant is removed due to the P&D technique. So only parameter left behind is a chemical shift. And the chemical shift, if we compare between hydrogen and C13 NMR, the normal delta scale for H1 is 0 to 10. While in case of C13, we have 0 to 200, and sometimes you may extend to 220 delta as well. We are taking the same standard tetramethylsilane, and the parameters which affect the chemical shift. The first parameter is electron withdrawing and donating inductive effect, diamagnetic anisotropic shielding and deshielding effect, electron donating and withdrawing resonance effect, which we also called as a mesomeric effect, and the last, which is very important, is substitution effect. Let us see some of the effects. Okay. So in column 1, you are observing aldehyde, aromatic molecules, olefinic molecules. Then we have the saturated molecules. Now coming to the H1, aldehydic protons come between 9 to 7 delta. Carbon-13 will appear between carbonyl carbon we are talking of. This carbonyl carbon will come between 210 to 180. Coming to aromatic protons, they are coming 8 to 6.5 delta, while aromatic carbons, they will resonate between 110 to 150. Olefinic protons are coming between 4 to 5.5 delta, while of that carbon, if we think it's 100 to 120. Then we have the methine carbon, which come between 60 to 85, while the hydrogen which attached to the methane, which is also attached to the oxygen, will have the delta value 4.4 to 5. Methylene group attached to the oxygen, if we take this substituent, it will come between 4.7 to 3.7. This is the delta value for the proton, while the carbon is coming 75 to 55. So whenever we have this electron withdrawing oxygen, electronegative oxygen, you can see delta value is very high as well for both H1 and C13. Coming to the hydrogen, which is attached to the carbon, then nitrogen. H1 will have the delta value 3.2, 2.8, while of that carbon is 70 to 50. Hydrogen attached to the olefinic carbon will have the value 2.5 to 3, while that of C13 will have the 90 to 60. So you have to compare the electron withdrawing atom, whether it is oxygen and nitrogen, and try to guess the values. Coming to the cyclopropane, this all the protons are coming in a shielded region. They will have the delta value 0.5 to 1 delta, while the carbon will be also shielded, and the carbon of cyclopropane is coming between 5 to 15. So these are the complete NMR spectra right from the 0 to 220. So at 0 to 20, you will see that saturated carbons are coming. Okay. The carbons which are attached to the saturated molecules, they are coming between 0 to 20. For olefinic region, will start from 100 to almost 120. So this will be olefinic, as well as aromatic protons will fall in the same region. Alkyne protons fall between alkenes and alkenes. They are coming between 60 to 80. Sorry, not proton, sorry, it's a carbon. And in between, depending on which atom is attached to that carbon, you may have the range of the delta values. Oxygen being a more electronegative, it will be that carbon is more de-shielded, while the nitrogen is less electronegative. It will appear a little bit towards the upfield. Coming to the carbonyl carbon, in between 190 to 200, we have the carbonyl of ketones and aldehyde, while esters, acid and amides, they are coming between 160 to 180 delta. These are the values. The carbon which is there in the saturated will come between 10 to 40. Methylene carbon 15 to 55. Methane carbon 20 to 60. Methylene carbon attached to the iodine 0 to 40. Methylene carbon attached to bromine 25 to 65. Methylene carbon attached to the chlorine 35 to 60. So as electronegativity increase, delta value also increases. Carbon present in alcohols come between 40 to 80. In ether, 40 to 80. Alkynes will be little bit shielded compared to the olefinic carbon. Aromatic carbon 110 to 160. Carbonyl of ester 160 to 180. Carbonyl of amide 165 to 180. Carbonyl of acid 165 to 185. While the carbonyl of aldehyde and ketones will come between 180 to 200 delta. We can observe the substituent effect in C13 NMR. In fact, in all the books, we have this equation that you must have seen during your MSc. You can predict delta value of alkanes, alkenes, aromatic compounds by having a different equations. This is for the hydrocarbons. Delta is equal to minus 2.5 plus summation of Na, where delta is predicted chemical shift, minus 2.5 is the chemical shift of methane carbon, while N is number of neighbor, A is additive parameter. So you may have the alpha, beta, gamma, and delta, different additives. This you have to, of course, take the values from the books and try to predict the values of alkanes. Uh, and methane will have minus 2.3, ethane carbon minus 5.7. The carbon of propane will be of two types. Methyl carbon is coming at 15, while methylene carbon 16. So you can calculate, of course, the delta value from this. So I will not spend the time on this. Let us move to the next. This is the DMF spectrum. In DMF, the structure we already seen over here. Uh, so at room temperature, okay, you just let me know how many types of carbon are there. One, methyl are same, and carbonyl carbon. So you should see the two, isn't it? Two carbon, only two peaks, which you are observing at high temperature like 150 degrees Celsius. Only two peaks. The peak around 32 is for the methyl, while the peak around 165 is for the carbonyl, which is there. But if you take the NMR at room temperature, you will see a three peaks. Why the three peaks? Because the nitrogen lone pair is resonate between carbon and nitrogen, and this pi electrons will move on oxygen. Okay, so you can write the second canonical structure where carbon nitrogen will have now double bond character. Due to double bond character, rotation is restricted. So these two methyls will be different. This methyl is cis to the oxygen. This methyl is trans to the oxygen. So electronic environment is different. So these two methyls are different. And this phenomena is called as a restricted rotation due to resonance effect. So two methyls are appear over here at room temperature. But at higher temperature, this higher temperature will be gives the energy sufficient which can rotate this carbon nitrogen bond, and hence to these two methyls will very speedily rotating, and two methyls will get same environment, hence you will get a single peak at high temperature. So you have to just remember whenever you are interpreting carbon-13 NMR, you just remember this kind of spectra, 8 to 30 carbons of methyl carbon, methylene carbon 20 to 45, methane carbon 30 to 60, and carbonyl carbon, and between there are very less range where you can remember, you can easily remember all this carbon and their predicted chemical shift. This is the H1 NMR. H1 NMR of the molecule which synthesized in my lab. So we can predict this H1 NMR by using the parameters like the integration, chemical shift, then we have the coupling constant. So all these parameters we can play and we can get the structure over here. So number of signal, position of signal, intensity of signal, and spin splitting will give the multiplicity over here. So all these parameters we have to take care when we are interpreting H1 NMR. While interpreting any NMR, you try to count the number of peaks. The number of peaks will be equal to number of non-equivalent nuclei. In H1 NMR, it will be proton, while in C13, it will be number of non-equivalent carbon. So number of signal is equal to number of non-equivalent carbon. The signal number of signal will be less only when the molecule has the symmetry. Okay. This example is appear in CSIR exam, which was held in 2017. Now the molecule they have given and they ask you the number of signal observed in a proton decoupled C13 NMR. So what will be the answer? You can write in a chat box. 5, 6, 10, 14. What could be the answer? This is biphenyl. Anybody? Which option is correct? Not able to see any example. Okay. So you have to draw the molecule in such a way that you can see all the types of carbon. Now you can imagine the plane which is passing through C5, C2, C1, C2 and C5 carbon. This carbon which divide whole molecule into two equal half and hence number of signals will be reduced to 5. Otherwise, number of carbon 6 plus 6, 12, 12 plus 4, 16. 16 carbon are there, but number of signals appear in C13 NMR are only 5 due to the symmetry element. Let us take the next example, 2-methyl pentane. How many signals would you expect? 1, 2, 3, 4. And these two are methyls are same. So the most intense peak is due to these two methyls. Coming to the 2-hexanol. Now here number of peaks will be equal to number of carbon because no symmetry is there. 1, 2, 3, 4, 5, 6. So 6 peaks you are observing. Hence it is a number of peak is equal to number of non-equivalent carbon. This is the 3-bromopentane. Total carbons are 5 carbon, but the signals are 3 because of symmetry. These two methyls are equivalent, these two methylines are equivalent, and they are coming over here. Coming to the hexane, one hexane, 6 type of carbon, 2 are olefinic carbons which fall between 100 to 140 delta, while other sp3 hybridized carbons, they are falling between below 50 delta. This is the natural product, eugenol. You can see the molecule very clearly and all the carbons are different. So total 6, 7, 8, 9 and 10. 10 picks should be there. Let us count over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 signals are you can observe. And you can easily find out sp3 hybridized carbon, which are this benzylic carbon and methoxycarbon are coming over here, while others are sp2 hybridized, they are coming above 100 delta. Coming to the carboxylic acid, here the example is pentanoic acid. It's a non-symmetric molecule, so number of carbon and number of peaks will be equal. Only the carbonyl carbon are coming around 180. Ester ethyl varilate, this carbonyl carbon is coming around 175. The rest of the carbons which are sp3 hybridized, they are coming below 60 delta. Amide carbons are coming also in the same region. These are ketone carbon which is most deshielded and coming around 220 delta, while rest of the saturated carbon or sp3 hybridized carbon are coming below 60. Aldehyde carbon are also coming more than 200 delta. Rest of the carbons are coming below 60. So for each unique carbon in a molecule, you will get a signal in C13 NMR. Only if signal number of signal are less, it's due to the symmetry. Let's say this is the 1,4-diethyl benzene. It has the symmetry which is passing through C1 to C4 carbon, which divide into equal half. So these two methyls are equal, these two methylines are equal, these two um, um, aromatic carbons, they are equal, while the CH carbons are equal. All other CH carbon are equals and they are coming over here, while methyl and methylene are coming over here. Coming to this phenolic compound, it has again a symmetry. So 2-methyl will be of equivalent. These two carbons are equivalent. These two carbons are equivalent. So let us count the total number of signal. 1, 2, 3, 4, 5, and 6. Yeah, 6 are there. Let us see number of signal over here. These two methyls are equivalent. Coming to the intensity of NMR peaks, we already know the first order analysis rules for the H1 NMR, isn't it? Equivalent protons will not couple each other, and number of lines, maximum number of lines you can calculate by using this formula, and intensity of these lines also you can calculate by using x plus 1 raised to n, where n is number of interacting nuclei, right? For n is equal to 1, the equation become x plus 1. You take the coefficient. So for doublet, you will get the intensity 1:1. Correct? This is the multiplicity and splitting pattern for 1H, 1H coupling for this molecule, ethyl, methyl ketone. The three types of hydrogens. So you will get the three peaks over here. The methyl will show you singlet. Other methyl will couple with the methylene, so we'll get the triplet, while the methylene protons will give the quartet, isn't it? And their intensity you can calculate by using the x plus 1 rule. So when n is equal to 1, that means if we have the only one, the neighboring carbon will have only one uh, proton, then x plus 1, n is equal to 1, you will get x plus 1 and the coefficient will be 1:1. So both the doublets will have of equal intensity. When n is equal to 2, you will get the intensity 1:2, 2:1. For carbon which has the 3, uh, n is equal to 3, the coupling nucleus, you will get the 4 lines in the intensity 1:2, 3:2, 3:1, and so on. And you can have the Pascal triangle to have the intensity when the both the hydrogens, they are coupling with each other, right? So intensities of the peaks with the multiplicity of the multiplets for the nucleus with I is equal to 1/2, you can either draw a Pascal triangle and get the intensity. This is for the both the interacting nuclei if they have the same spin. Okay. Coming to the carbon 13. Before carbon 13, let us have one more example in addition. Suppose hydrogen uh, is interacting with the deuterium which is attached to the neighboring carbon. Now the spin number is different. For H1 it's a 1/2, for deuterium it's a 1. Then for such kind of molecule you can calculate intensity of the multiplet like this. If the neighboring carbon has only one deuterium, deuterium has spin quantum number 1, you can get triplet in the intensity 1s2, 1s2, 1. If we have n is equal to 2 deuterium, though if you have the two atoms of deuterium which are coupling with the hydrogen, you will get the 5 lines in the intensity 1s2, 2s2, 3s2, 2s2, 1. If we have 3 and 4, you can develop this Pascal triangle to get the intensity. Now this Pascal triangle you can use only when the coupling nuclei will have the different spin quantum number, 1/2 and 1. So this is one question they have asked in the CSR exam in 2012. The H1 NMR spectrum of HD shows a singlet, triplet, or doublet or triplet with the intensity 1s to 1. Now hydrogen has the spin 1/2, deuterium is 1. So you can use the formula to calculate first number of lines by using the formula 2ni plus 1. Now n is single because we have single deuterium, so n is equal to 1. Filling in this equation, you will get the 3 lines. Now deuterium has the spin 1 and hydrogen is 1/2. So use this Pascal triangle and you will get the intensity 1s2, 1s to 1. So the last option, option D, a triplet with intensity ratio 1s to 1s to 1 is correct. Again in June 2017 in CSIR exam, they have asked the question, C13 NMR spectrum of DMSO D6 gives the signal at 39.7 ppm as singlet, triplet, quintet or septet. So how do you can calculate? First of all, whether you know the structure of DMSO, I hope everybody knows the structure of DMSO. It will be a CD3, CD3, SO, CD3. Now this carbon is attached to how many deuterium? 3 deuterium. So in order to calculate number of line, use this formula 2Ni plus 1. So N is equal to 3. You will get total 2 into 3 into plus 1. You will get 7 lines. So septet you should get and use the same triangle that we have seen. This triangle. This is for n is equal to 1. This is for n is equal to 2. This is for n is equal to 3. So you will get the intensity as 1s2, 3s2, 6s2, 7s2, 6s2, 3s2, 1. So you don't have to remember the values. You have to just develop this Pascal triangle. This is another Pascal triangle than the this one. This one is different. You can easily uh, get this Pascal triangle by having this value. One you have to drag over this one, you have to drag over here. From this 1 and 1, you will get the middle values. Similarly, for 1 plus 2, you will get this. But this is little bit different. So you try to remember this both the Pascal triangle and get the intensities of multiplet. Again, in 2014, they have asked one more question on relative intensities of carbon signal for CD3Cl. Okay, deteriorated methyl chloride. Now, again, here this carbon is attached to the 3 deuterium. So 7 lines you will get. So option D will be the correct one. I hope now you understood how to calculate number of lines and their intensities. When two coupling nuclei will have the different spin quantum numbers. Coming to the enantiomer topic and diastereotopic carbons. Now here, these two methyls will be equivalent and they are coming at the same place over here. Correct? So they are called as enantiotopic methyl. How to get the topicity? You just replace one methyl by one phantom atom and try to have the structure, replace the other methyl, try to get the other structure and correlate both the structures. So they will be enantiomers of each other. So these two methyls are enantiotopic, and the enantiotopic methyls will appear at the same position in C13 NMR. Coming to the other molecule, now these methyls will be distereotopic and you will get a separate signal for these two methyls. So topicity you can easily find out in carbon 13. These are the of uh, examples of the molecules that you can do at the homework. Find out the number of signals for these molecules. Okay, the last molecules is gyrenol. Let us see all these carbons are different or not. Count the number of carbon: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons are there. Let us count over here: 1, 2, 3, 4, 5, 6, 7, 8, 9. Is it one carbon is missing? No, it is not missing. One carbon is hiding over here. Okay, we will do the assignment of carbons of gyrenol. 8 and 9, you can find out that these carbons are attached to the sp2 hybridized carbon. So number of carbons are 10. Number of signals are this. So 8 and 9s are carbons that have the chemical shift between 15 to 25 delta. One more technique which are oftenly used in C13 NMR, which we call as off resonance technique. Now in P&D spectrum, we have removed all the H1 coupling with the carbon, but in off resonance technique, a sample is irradiated with the two different radio frequency. One will excite carbon 13 nucleus and the second RF or pulse is set between 500 to 1000 hertz away from the TMS of H1 to remove geminal, vicinal and long range coupling. So what happened due to that? Only a direct coupling or 1-2 bond coupling is remaining, is restored, but in reduced form. Their coupling constant is also reduced. So actually, if you see the coupling between carbon and hydrogen of saturated carbon is found to be 150 hertz, but with off resonance, we have reduced to 20 hertz. So coupling constant is also reduced in off resonance coupling. So what happens due to this? Any more information we will get in off resonance technique? Yes. If methyl is there, this carbon will give you quartet. Methylene carbon will give you triplet. Methine carbon will give you doublet. While the quaternary and substituted carbon will give you the singlet. Okay. So in off resonance technique, you can easily find out the methylene, methine carbon, and fully substituted or quaternary carbon. But this off resonance technique will take little more time. So these are the number of carbons, number of signals that get it from the off resonance technique. Methyl carbon quartet. So let us look at the proton couple spectrum of ethyl phenyl acetate. The structure is given over here. This is proton couple. So this methyl will appear as a quartet. This methylene appear as a triplet. This methylene is appear as a triplet. And the aromatic region is due to the coupling pattern, it is difficult to interpret. Okay. So here is the example of P&D spectra, where we have removed all the coupling of hydrogen. So you will get 1, 2, 3, 4, 5, 6, 6 carbons. In off resonance spectrum, in fact, the methyl will coming as a quartet, methylene will coming as a triplet. Correct? And quaternary carbon will come as a singlet, while the methine carbon will come as a doublet. This is again a PND and off resonance spectra for 1,2 disubstituted aromatic compound. You can this is only for your understanding the difference between PND and off resonance spectrum. So students, you must be knowing what we are doing in one dimension to get the one dimension NMR spectrum. The signal intensity is plotted as a function of chemical shift. So we have the on x-axis we have the chemical shift and y-axis will be the intensity. Okay. Now this is achieved by normal 90-degree excitation pulse immediately by the data acquisition. That data we are storing in computer and converted into a frequency domain spectra by Fourier transformation technique. And this sequence we are repeating again and again to get a intense peak in spectrum. Now, when we are moving from 1D to 2D, 3D spectrum, there is a we have to develop a pulse sequence. So more complex pulse sequence are used in Fourier transform NMR. Uh, all the nuclei present in a molecule we are exciting at one time, and we are giving the pulse for a few seconds. The pulse can be transmitted along any Cartesian axis, and the pulse can be transmitted with varying duration from micro to few seconds. Pulse can be programmed into a sequence, and the result of pulse program is different nuclei may exchange energies. Nuclei may affect each other relaxation time. Nuclei encode information about the chemical shift as well as homo and heteronuclear spin coupling. And this lead to development of more advanced technique in NMR like the 2D and 3D NMR. So one of the technique which is frequently we use is DEPT technique instead of off resonance technique, which require very more or little more time. The DEPT technique require less time. The information from DEPT technique is also same as the off resonance technique. Now, what is DEPT? Is distortion less enhancement by polarization transform. The DEPT, before DEPT, we have one more technique which we call as attached proton test, which gives the number of proton attached to that carbon. The complex program of pulse sequence and delay times is required for both carbon 13 and H1 channels, and this result in different phases of carbon atoms from 1 to 2 to 3 attached hydrogen. And the phases of these different carbons depend on the duration of delay in a pulse program. So there are three DEPT programs you can use: DEPT 45, DEPT 90, and DEPT 135. In DEPT 45, only a quaternary, okay, all these DEPT program, quaternary carbons will not be observed. In DEPT 45, only the carbon which has the attached to a hydrogen atoms will produce a peak. DPT 90 will give the carbon, will give the peak for the carbon that are attached to only one hydrogen, that is methane. carbon will show signal in DEPT 90. While DEPT 135, you will see the methine and methyl carbon will be the positive peak while methylene will be the negative. You understood the difference between these three, all the three DPT? In DPT 45, all carbons will give the signal except quaternary. While DPT 90, you will get only methine carbon. While DPT 135, you will get methine, methyl positive and methylene will be negative. Here I have shown the DPT spectra of isopentyl acetate normal peak. This is the how many carbons are there. These two methyls are equivalent. So one signal you will get from this 1, 2, 3, 4, 5, 6. Let us count over here. Yeah, 6 signals, 6 peaks you are getting in carbon 13 P&D spectra. Photon, noise, decoupled spectra. Now DEPT 45, quaternary carbons will be vanished. So you will not get the peak due to the C5. So all rest 5 peaks will be appear over here. In DEPT 90, only methine carbons will be appearing. So how many methynes carbon are there? 1. Yeah, so only one peak will be there. In DBT 135, methylene carbon will be down. So how many methylene are there? Only one. So with that is down. Sorry, two methylene groups are there. So two peaks are down while others are positive. Please remember in DPT you will not see quaternary carbons. Let us see one more example over here. Total number of carbons are 8, but let us count the number of signal. There are 8. Yes, there are 8. Try to assign the signal. You can easily assign the signal for olefinic carbon because they are de-shielded, out of which 6 carbon is it will have the more chemical shift because it is attached to a substituent, two substituent, 7 and 8 and 5. So it will be more de-shielded. It will have more delta value compared to the 5. Okay. And other reason is of intensity. You can see here the 6 carbon is does not have any carbon, any hydrogen. So intensity is less, but due to NOE effect, this carbon intensity is high and you will easily find out 6 and 5. Next, the carbon 2 is attached to the oxygen. So as oxygen is electron withdrawing, so inductive effect will be there and C2 will be de-shielded and come around 70 delta. Okay, so we have found out 6, 5, 2. Let us now worry about 3, 4, 1 and 7, 8. So how to get it? This. You can easily get 4 carbon because it is the next de-shielded carbon attached to the olefinic carbon. So the signal which is coming at 40 is due to the C4 carbon. C1 can be easily find out because it is coming below 20. It is most shielded signal. Now the left behind between the C3, C7 and C8 and they are coming over here. So how to assign chemical shift to C3, C7 and C8 carbon? You can do the DPT. In DPT, the C3 carbon will give the negative signal. So, and methyl will give the positive signal. So this is the DPT for the same compound. Now you can easily assign 7, 3 and 8. So in this way, DPT will help you to assign the chemical shift to each carbon. The same is with the citronol. Citronol contain total 10 carbons. The signals are there. DPT will able to help you to assign all the carbons. So please remember in DPT, this is the normal C13 spectra. In DPT, you will get All the carbon which has the hydrogen will come as a positive signal. Quaternary will not appear. In DPT 90, only the methane carbon will come, while in DPT 135, methyl and methylene will be positive, while methyl and methane will be positive and methylene will be negative. Again, this is the example of ethyl phenyl acetate, which shows which we can assign exactly C chemical shift to all the carbon by using DPT technique. This is the more complex molecule material product codenine. The DPT technique is, of course, will help to assign all the carbon. At homework, you can take this structure, epsilon, and predict its C13, DPT 90, and DPT 135, how the peaks will looks like. You can also predict the chemical shift of this molecule. Okay, this is the DPT of epsilon, normal C13 NMRs, P&D, DPT 135 and DPT 90. In DPT 135, you can see C5, C3, C8, C10. This all methylene will be down. Okay. So irrespective of the carbon, which carbon it is, sp3 or sp2. If it is a methylene, they are coming down. You can take screenshot of this molecule and find out the number and appearance in DPT. Okay. So most of the things I have taken from the MSc program. Let us try to deduce the structure of this molecule. We have the molecular formula C5H10O3. IR has been given, H1 NMR has been given, C13 NMR has been given, and DPT 90 and DPT 135. Your time start now. You please give the structure of this molecule within 2 minutes. Very simple molecule. Yes, please. Tell me what you will get the information from what? Okay, from molecular formula, what you will get? Site of unsaturation. So please calculate site of unsaturation. If there are 5 carbon, to get the saturated molecule, how many hydrogen you will need? 12, but there are 10. So 2 hydrogen are less, so one site of unsaturation. 1720 indicate carbonyl stretching frequency. Coming to the H1, we have 3 peaks. So there are 3 kind of hydrogens, correct? Coming to the signal at 3.5, at 3.5 is for 6 hydrogen, 4.6 is highly de-shielded proton coming at 4.6 with the singlet. That means it does not, its neighboring carbon will not carry any hydrogen. Carbon 13 shows a 4 kind of hydrogen. So there are 2 methyl groups which are equivalent. 204 indicate ketone carbonyl or aldehyde carbonyl, but aldehyde protons is not coming over here. So aldehyde, that probability we have ruled out. So 204 is due to the ketone carbonyl. So left behind 25, 55 and 100. Out of this 25, 55, 104 are all up signal, isn't it? And 104 is in DPT 90, it's up, so it's due to the methane. So by taking all this information, the structure of the compound is shown over here. This is easier, isn't it? So let us move to the next. Deduce the structure of the compound with the molecular formula C8H16O3 from H1C13 and DEPT technique. Please let me know. This is your homework. You will see that one negative peaks appear at 60, so it may be the CH2, while the positive peak may contain methyl and methyl. Site of unsaturation, how many are there? It contains one site of unsaturation. 3500 to 36 indicate OH stretching. 1730 indicate carbonyl, but carbonyl of what? It's a very high frequency, so it may be due to the ester carbonyl. Next, you have the three protons, which shows the doublet. So methyl group attached to a carbon which carries only a single hydrogen. Correct? Next, we have 117 and 1.17, 1.18 singlet for three protons. So two methyls are present over there. At 1.27, you have the triplet for three protons. So again, you have the CH3 attached to a CH2 because it is a triplet signal. Next, 2.7 broad singlet, one hydrogen. It may be due to the OH signal because in IR also we are observing OH stretching frequency. So 2.7 can be a OH. So we will write all the fractions part of the molecule, structure of the molecule. 3.86, one proton quartet. That means we have the CH attached to a CH3. Next, quartet, again you are getting, but it's due to the two protons. So you will get CH2 attached to a CH3. Okay, now please remember this quartet is coming at 4.1. That means it must be attached to a oxygen. So let us draw this there. 1730 indicate ester carbonyl. So I am writing that also. Okay. Okay. Let us join all these fragments. Before that, DPT 135 you indicate that one methylene is present, and here also you are observing one methylene is present over here. So 4.17 is coupling with 1.27, isn't it? Because at 1.27 we have the triplet signal, which you can get it only when we have the methylene. So 1.27 is coupling with 4.17. This information you are getting. So part of the structure will be CH3. Let us try to write one end of the molecule attached to the CH2 attached to the oxygen, right? We have the ester, so I will write again one carbonyl group. Okay. Next. What other information we can get it? Now 1.5 1.15, it shows a doublet. 3.86 is for the one proton, it shows the quartet. So 1.15 is coupling with 3.86. Now 3.86 is the next deshielded signal, correct? So the part of the structure, this is further attached to a oxygen. This methyl is further attached to a oxygen, which we have predicted OH from the IR frequency. Further, we have the two methyl groups. Okay. So by having this, okay, so the other end we are getting over here. Left behind two methyl groups. These are the two methyl groups which we have not assigned, correct? So the structure can be a two methyls, CH, OH, and further methyl. These two methyls, they are not equivalent, chemically equivalent, because they are attached to the carbon which is attached to four different groups. One is OH, one is methyl, hydrogen, and this. So this carbon become a asymmetric carbon. So hence these two methyl become a distereotopic and they are coming at 1.17 and 1.8. So this is the structure of molecule. I hope everybody able to get the structure. Okay. This is the Central Instrumentation Facility, which is constituted at Savitribai Phule Pune University campus. We have the instrument like the LCMS. We have LCMS-MS, we have GCMS-MS, then we have 500 megahertz NMR, we have confocal microscope, we have the XRD, but it is under maintenance over here. We have the spectropolarimeter, CD spectropolarimeter, then thermophoresis, we have ICP-MS, we have PPMS, and AFM, and recently we have also in January 2025, we have constituted this XRD as well at our facility. So these instruments are very, very sophisticated, almost 15 to 20 crore instruments total value if you take, because just only with the NMR, we have bought it in 2014. That time its cost was 3.5 crores. Now it must be more than 6 crores. So this is the NMR facility at SPPU. If time permit, you please visit our facility at the SPPU and please use it for your research purpose. Thank you all of you for your patience. Thank you. If you have any query, I'm happy.
Any questions for the participants?
No question? All are silent?
No questions?
Anytime you can approach me if you have any difficulty for getting the data or for interpretation as well. Hello? I think you kept all the participant on mute or what?
On behalf of the organizing committee, and sincerely thanks Dr. Vaishali Shinde for giving an informative and valuable lectures on nuclear magnetic resonance. Dr. Shinde's clear explanation, expert guidance, and research-focused approach very helpful, especially for our PhD scholars. Her ability to link basic principles with advanced application of NMR has improved our understanding and will greatly support the scholars in their current and future research work. Thank you, ma'am.
Yes, thank you. Thank you. I will leave the link.
कोणाचं प्रेझेंटेशन बाकी आहे आज?